Okay, hi everybody, welcome back to Topics in Gravity. So I'll just launch right into it. So today I hope to be able to, well, essentially finish this discussion on effective gravity in flat space, although I'm not so confident, maybe we'll need a little bit of next time. And so I want to basically pick up right where I left last time, which is this effective field theory logic, and then launch into applying it in particular to the effective field theory that, well, effective field theory of gravity, basically. So let me just begin again by reminding you in a few steps what our EFT logic was that we seek to apply. So, so that's our EFT logic. I mean, I should ask, you can all hear me, yes?
Perfectly, yes.
Yes.
Good. Okay,
Yes.
great. So as we were saying, we should anyway be content to calculate to a certain accuracy. So let's say choose desired accuracy. Let's say 1% or something. Okay. And then we're going to go and see what that means for the order in this E over M expansion. So what do I mean by that? So this determines order in the, so E is the energy of the process that we're interested in, and M is this parameter that controls the EFT, order in E over M. And so, of course, that depends on what energy we're interested in, and it also depends on what theory we use. So this E is, of course, the energy, and M, whatever is this parameter, and what value it takes depends on the theory that we're using. So a natural choice for this parameter in the context of gravity, for example, would be the Planck mass, but it is not forced to be the Planck mass, but you understand the Planck mass would be a natural one. So then we use power counting to identify all ON that can contribute. So we use power counting, and that gives us all the operators, the set of all operators, denoting as ON, that can contribute. And in particular, this is a finite set. And then in the fourth step, well, there is two ways. Either we are in this case where we know the UV theory, which we discussed briefly last time. So let's say UV is known. Okay. Then we can just calculate all the, well, we can attempt to calculate, even in a known theory, this may be very complicated, but in principle, we can calculate the coefficients of these operators Cn. Okay, to the desired accuracy by matching, let's say. And then the point is that once we've calculated these coefficients, now we can calculate low energy processes in a much streamlined way. So this is the advantage. I mean, even though we can calculate in this theory, even in principle, we can simplify our task for low energy processes, in fact, considerably by just reducing it to a set of coefficients. So, and then for B, this is if the UV is not known. If UV is unknown, or of course, if, you know, in the subcase of 4A, where this is known in principle, but in practice it's just too hard to do. So unknown or too complicated. Then we can determine the finite set that we need. These coefficients by comparison with amplitudes. Okay, so let's say there's capital N of them of n judiciously chosen amplitudes to data, let's say, experimental data. Okay, and then of course the point is that what remains, the theory, the theory so determined is a predictive theory. After we've done this, fully predictive theory. Okay, so a famous example of 4B. Well, actually, I mean, yes, both of our examples of 4B. So of course, the prime one that concerns us is gravity, but then there's also the pion effective Lagrangian that gives you the low energy physics of QCD. This is in principle in 4A, but of course we don't really know how to arrive at it in practice from the QCD Lagrangian itself. So we use it in the same way as we would use 4B, and it is extremely successful. All right, so now that's just the reminder of the logic of EFT as we laid it out. And so now let's go and apply it to gravity. That's really the next step. But maybe I can also pause if there are any questions on your side. Okay, excellent. So let's do the power counting for gravity. So this essentially is now our study of, if you want, low energy quantum gravity in flat space. Well, this begins our study of this. So first of all, the degrees of freedom, the low energy degrees of freedom that we identify, that's the metric, or rather the fluctuation of the metric. Okay, so we decompose the metric into our background Minkowski plus the fluctuation h mu nu, which is essentially the graviton. And then the symmetry that we impose is basically we combine locality and this Lorentz invariance, which we said leads to basically the requirement that we should have a theory that is invariant under diffeos. And now, instead of doing this exercise that we did in the classical theory, where we still built a nonlinear theory, but of two derivative gravity, what we're going to do is we're going to take this EFT action on board, and we say that, okay, obviously we can also get high derivative terms, but those should also be diffeo invariant by our symmetry analysis. So we're going now to basically arrange these terms, the possible terms, arrange the action in an energy derivative expansion, right? So in the Lorentz invariant case, this is the same thing, right? The derivative expansion and the 1 over energy the energy expansion, excuse me. So we will just write down something like the Lagrangian of our EFT is going to be, well, we have this guy, we have the cosmological constant, then we have the two derivative term, which is the Ricci scalar, and then we get curvature squared terms. So I'm giving them arbitrary coefficients. We're going to work on these coefficients to simplify our life a bit, because there's actually quite a lot that can be done in gravity. But for now, these are just coefficients. I guess let me continue here. So we have A3. I'm just going to write a bunch of terms. So this is like sigma rho sigma r mu nu rho sigma the Riemann squared. And then we go to the order of curvature cubed interactions. I mean, I'm just giving you examples, okay? So a curvature cubed interaction, for example, then will come with some extra scale. I'll comment in a second while I give this a different letter. And then we also have, for example, we could have a coefficient like the two derivatives acting on R, okay, which is the same derivative order as this Riemann squared, which is why I wrote it there, and so on and so forth. So before getting overly systematic about these terms, I want to actually basically give you a bunch of ways that you can simplify this task and that you can make your life easier. But here I just want to illustrate the kind of terms that we're going to consider. So first of all, this M, okay, so this defines what we call low energy. So of course one could, if one wanted to, take this to be the Planck mass, but one isn't required to do so. For example, it could also be, if we were interested in very low energy processes, one could also put this to be the mass of the electron, or anything else really. And in fact, when we go to things like string theory, the fact that we have M Planck and the second scale is going to be very natural, and the second scale is going to be, as we see, associated with what's called the string length. But at any rate, in principle, remember we had in our EFT Lagrangian, we had this F, which gave us the overall dimension. That's like a combination here of M Planck and M. And then we had the parameter that gives us the cutoff that was in principle independent. And that's now our little m here. And I'm going to keep it general. Once we do the power counting, you see exactly what is F and what is the other scale in terms of M Planck and little m. And then I'm also going to point out in some specific applications, such as the effective expansion of string theory, for example, what is this little m. But now, let me go a little bit over the different terms that we have here. So the most glaring one that we should first address is this cosmological constant term here, lambda. So actually, let me give this its own, so the cosmological constant. So, okay. So for the cosmological constant, right, one often sees this thing that lambda should be order 1 by EFT logic. Of course, now we should be a little bit more precise about what units this should be in, so by EFT logic. So often you see the normalization, the way that people write this Lagrangian, right? So lambda has no derivatives. So in order to be of dimension 4, there really should be some, there really should be a dimensionless, dimensionful constant, basically the Planck mass to some power, okay? So the normalization that we usually see and that we can compare to statements is that LEFT is actually something like minus G times R minus 2 lambda, which I now call tilde, plus dot, 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 and then you have this M Planck squared over 2 outside, okay? But since there is 2 derivatives between lambda tilde and R, the units in which lambda tilde really is order 1 itself is of order M Planck squared. So if lambda in the natural units is order 1, this means that what I want to say is that lambda tilde EFT, okay, is order M Planck squared, right? Because you have to make up the difference in dimension between these two. And of course, the natural thing here is M Planck squared. And if we evaluate that, so this is basically the EFT prescription or prediction, let's say, right? Every operator in the derivative expansion that can be there should be there and should be there, order 1 in natural units. So this, if I evaluate it, is something like 6 times 10 to the 54 electron volt squared. And this is essentially, well, we can say, we can even put a box around it. Okay, this would be the EFT prediction. Okay, I hope you are following this. I have not done anything particularly special. I've just said that any term in the derivative expansion up to a given order in derivatives should be present. If it's not present, then will be generated by loop effects. And the coefficient with which it is generated is generally of order 1 in the correct unit. So if you have the coupling constant to be dimensionless, it's order 1. So we have to put here the powers of m Planck squared to make up for it. If we evaluate it, we get that this lambda tilde that people usually quote in the literature is of order 6 times 10 to the 54. And then, of course, now, however, lambda tilde experiment is actually 10 to the minus 66 electron volt squared. Okay, this is the best fit of lambda CDM, at least when I looked it up last.
Sorry,
And
I
so,
don't think I fully follow. Can I ask a question?
Yeah, one sec. So this is 120 orders of magnitude off. Yes.
So is lambda, is that m Planck squared times lambda tilde?
So what was I saying here? So here lambda, this lambda would be naturally of order m Planck to the 4th, right?
Oh.
Because yes. So okay. So this lambda would be naturally of order m Planck to the 4th because, well, that's, as I said, that's the natural dimension that you have. You have a dimension 4 object here. Okay.
Okay. Yeah.
So so order 1 in units. Yeah, I said here the natural units that you should choose, but the units here are m Planck to the 4th. Okay, sorry, this was written indeed in a somewhat confusing way. Let me. Okay. Let's see if I can arrange this in some way. Yep. Right, because you have it standing out here, so this has to have mass to the 4th, and it's order 1 in those units. But the thing that people compare most of the time, the number that they quote is when they normalize the Lagrangian like this. That's lambda tilde, okay? But now lambda tilde already has this, is multiplied by m Planck squared. So this is order m Planck squared by that logic. And if I evaluate that, I get my 10 to the 54. And that's the thing that I can compare to what's usually quoted in the literature, because what's quoted in the literature is compared to this normalization. Okay.
Yeah.
Thanks for picking that up, though. And so, yeah, so that's a mismatch of 120 orders of magnitude, which is, of course, what is known as the cosmological constant problem. And I mean, I suppose to put in a little bit of philosophy here, we really have no idea how to solve this. This is a huge problem of the same kind as the hierarchy problem, and we have absolutely no idea how to solve it. And so that's always been, in some sense, in tension with all these arguments that we need to solve the hierarchy problem using some sort of a natural way, because it doesn't seem to be the case for the cosmological constant problem. So we have no good idea how to, let's say, solve this, right? Except with fine-tuning. Of course, also with entropics, but that's not really going to be part of this course. And so in this course, we basically choose to fine-tune the cosmological constant. So we tune the bare parameters such that indeed, for the first part of this course, which is actually about to be finished, we set it to be 0. Okay. So this is a massive fine-tuning, as you have now, of course, seen again. And for the second part, when we work in ADS, we take it to be negative. So lambda is equal to lambda ADS, which is a negative cosmological constant. And here we also actually just tune it by fiat, because we have to match some parameters in the gauge theory. But I just wanted to give that little discussion, because once you start writing down this EFT logic for a Lagrangian, then the most glaring thing is that you're basically immediately tuning away the most relevant operator. And okay, this is what we have to do, because otherwise we would be, you know, contradicting experiments by 120 orders of magnitude. Okay, now let's therefore, so we've therefore now already reduced the Lagrangian that we work with to something like, we start with m Planck squared over 2r. And now we're going to look at curvature squared interactions. Well, it's, yeah, so Riemann squared rho sigma, r mu nu rho sigma. And then we have something like curvature cube interactions, which are suppressed. And we also had this derivative interaction, but let me not write it. So now let's go and before doing anything like power counting and so on, let me show you how to whittle down some of these terms, which is going to be a mix of general EFT reasoning and also things that are specific to gravity. So redundant interactions. And then we're going to conclude by saying something about one loop counterterms. So in 4D gravity, there is this theorem that you can write the Euler number, chi of m of some manifold. So this is the Euler number. You can write this as some integral in the right normalization, 32 pi squared, times integral over the manifold of its metric, times a certain combination of curvature squared terms. So r mu nu rho sigma, r mu nu rho sigma, minus 4 r mu nu plus r squared. This is called the well, this is the Euler density, of course, also known as the Gauss-Bonnet term. Okay, and this thing has to be a total derivative by virtue of giving you a topological invariant of the manifold. And so since it's topological, okay, this means that it does not respond to metric fluctuations. So it doesn't respond to metric fluctuations. Okay, I mean this is really the same thing, right? We always say a topological term is something that doesn't depend on smooth deformations of the manifold, and in fact the graviton is precisely that. It's a small smooth deformation of the manifold, so this term doesn't care about it. Okay, and so what that means is, so it doesn't respond to metric fluctuations, and you know, i.e. it doesn't contribute to graviton amplitudes. So what that means in practice is that I can, for just convenience, I can shift the Gauss. I can add the Gauss-Bonnet term with any coefficient I want to my Lagrangian, and I don't change the amplitudes for the gravitons. And so that means that I can shift any coefficient of. I can either shift the coefficient of this or of this or of this to 0, right? That will shift a little bit the coefficients of the remaining terms, but that's not so important. But in particular, I can get rid of one of these interactions. So for example, that we're going to make the choice that this tells us that we can drop the Riemann squared term, for example. Okay. So we're going to set A3 is equal to 0 here. Okay, but of course we could have also dropped, as I was saying, A1 or A2. That's not important, but we're going to make this choice. Now the term that I haven't written, okay, maybe I should just write it one more time, because now I'm going to say something about that guy. So we had also C1 times, okay, this guy. So that also is a total derivative. Minus G times the D'Alembert operator acting on R, for example. This actually can be written as just d mu of minus G d mu R. I'm just being a little bit overcomplete here. This is, of course, also just an ordinary derivative. So this is a total derivative. It's total derivative, okay? And why is that? Because you can write the covariant, you can write the convariant Laplacian as something like, you know, 1 over G d mu G d mu. So if I multiply that with this factor of G, oops, right? Then the two metric densities cancel, and I'm indeed left with this sort of total derivative here, okay? And so this means actually, this also means that I can drop, for example, C1. I mean, not for example, in this case, I can drop C1. And one way you can see it is also that if you write down the Feynman rules for such a total derivative term, then you always get the sum of all momenta as an overall factor, but you know that the sum of all momenta always gives 0 because of momentum conservation. And so you can drop any such term from any Feynman amplitudes. I mean, it just contributes 0. So, fine. So this was some specifics about the structure of these terms. Okay, so as I said, we're going to do now a mix of sort of general EFT reasoning and something that's specific to the structure of the Einstein EFT. So up to this point, right now, we've done two things that are specific to the Einstein EFT. And by the way, of course, we've also worked up to curvature cubed interactions. So, and also this two derivative acting on R and so on. Of course, if you went to higher orders, you could do more such maneuvers. But essentially, you would eliminate things that are total derivatives. But now let us eliminate some further things, and let's do it specific to gravity. But this is now something that is something that you can always do in an effective field theory. You will see why. And the reason why you can always do this in an effective field theory is that this has to do with the fact that you arrange it in derivatives. So you can do field.
Can you repeat your last point in the previous slide? Because I missed the questions.
Sorry, which last point? I mean, I can use the fact that this term is a total derivative to eliminate the coefficient C1, because it will not contribute to graviton amplitudes.
Okay, yeah, sorry, thanks. I just missed the
question. Yeah, no problem. But that was the point that you missed?
Yeah, exactly.
Yeah,
it was
yeah.
just
Okay, excellent. Yeah, excellent.
Okay, thank you very much.
Yeah, sure. And I was making the point that, I mean, the fact that these terms can be written as total derivatives, here, this specific term, this had to do precisely with the way that the covariant Laplacian, the D'Alembert, sorry, covariant D'Alembert operator acts on the curvature invariant R. Okay, but now, so field redefinition is something that can be done for any effective field theory, and it has really to do with the fact that what you do is you do a derivative expansion. So what we do is let's just consider redefining the lowest order metric to G mu nu plus Y mu nu. Okay, then the change in this term, let's see the change in the lowest order term. So d4 minus, oops, d4x minus gr. Okay, this change is now, of course, we all know how to write this if we've ever derived the Einstein equations. This is equal to the Einstein tensor, so Ricci minus 1/2 Ricci scalar G mu nu contracted into Y mu nu. Okay. But now look at this. So if I now choose Y mu nu, for example, to be the Ricci tensor itself, then what I get is I get something like a Ricci squared here. Okay. And here I'm going to get a Ricci scalar squared type term. So if we choose the following: m Planck squared y mu nu, this is just a convenient way of writing it, is 2a2 times the Ricci tensor minus a2 plus 2a1 r g mu nu. Then we can eliminate actually r squared and r mu nu terms from the EFT Lagrangian. Okay, so that means that we can actually also, let me just say this before I say a few more words about, we can also say A1 and A2 are equal to 0. Let me check if I remember the right terms. Yes, so we can also drop the r squared and the Ricci tensor squared contribution. Okay, and so what does that really mean? Well, why can we just do this? Well, you see, the point is, so this is something like, as I was saying, this is a general EFT principle. Okay, how to say? Because you're truncating by construction at a given order in derivatives. Okay, that means that what happens at the next order in derivatives and higher, you're just ignoring. Because you're ignoring it for good physical reasons, in some sense, you can shift all of your worries to higher derivatives. Okay, so what happens then is if you redefine what you call the lowest order fields, for example, by terms that are proportional to derivative interactions, you see, we shifted this lowest order term by adding something which is second order in derivatives. Okay, then you generate terms that are higher order in derivatives, and that shifts the coefficients of what's higher order in derivatives. And you can use this to basically identify the set of coefficients which are, if you want, invariants under those shifts. And those need to be the ones that are physically relevant at the given order in derivatives. And of course, you apply this shift everywhere, but you don't care what happens to the higher order terms because you're ignoring them anyway. Okay, so you can then choose them in such a way that they do something convenient at the order that you're calculating. Okay, you can always do that. And another way of saying it is that you can always eliminate terms which vanish on the lowest order equations of motion. So you can always eliminate terms from the EFT, terms that vanish on, let's say, lowest order equations of motion. And the way that you do this mathematically is you choose field redefinitions. Okay, because the field redefinition basically precisely shifts you by the lowest order equations of motion, as we have seen here. So this you can do in every effective field theory, but in this gravity effective field theory, I've demonstrated to you that we can find a field redefinition which allows us to get rid of the remaining curvature squared terms. So this is actually a very important realization. This means that if you have pure gravity, then our effective Lagrangian contains no curvature squared. Let me just write it like this. Curvature squared interactions. Okay. So in pure, let me just underline this. In pure gravity, okay. So this means that the first correction is order r cubed, and this has the important implication that you also cannot write down a physical counter term at order r squared, which means there can't be divergences at order r squared, which actually means that no one loop counter term which is actually equivalent to the statement which has been in a painful calculation in some sense predicted by 't Hooft and Veltman. This was before people were using this EFT logic. Pure gravity actually has no one loop divergence, is finite at one loop. Pure gravity is finite at one loop. But of course, so this was at the time an exciting discovery because, you know, one might not have expected this to be the case, but there is immediately two bad pieces of news. One is that, okay, this is only true at one loop and there is a physical divergence at higher loops. But secondly, also it's only true for pure gravity because you see, if you have matter, then on shell, we don't have Einstein tensor is equal to 0, but we have Einstein tensor is equal to the matter T mu nu, and we couldn't have done this field redefinition. And indeed, if you couple matter to gravity, then there is a one loop physical divergence. Okay, so this is why I underlined here pure gravity. But for the time being, we work in pure gravity. And for us, this conclusion, I mean, we don't even have to talk about all of these, sorry, we don't have to talk about these sort of, these statements here. Okay, for us, the conclusion is simply that we can use the structure of the derivative expansion to get rid of two of the curvature squared interactions. And we were able to use the Gauss-Bonnet theorem, meaning that a certain combination of the three curvature squared interactions is topological to eliminate the remaining one. And so we can indeed eliminate all three curvature squared interactions before having done any calculations. Okay. Now, yes.
Is the redefinition that you define, I mean, the change in the action under redefinition, is it an exact answer?
No, but it doesn't matter, because if there is higher order terms, so terms, for example, y mu nu squared, those are at higher order in the derivative expansion.
I see. Okay.
Okay. So right. So now let's do the power counting. So this was some general arguments as to how we can simplify our life anyway. Okay, but now let's get down to it and let's do the power counting.
Question?
Yes.
Is there also a field redefinition trick for curvature cubed terms? Or for part of them?
Yeah, let me think. Yes, sure. Yes, you could shift also by something that's proportional to curvature squared terms, and that would change the structure there, right? So if I had, right now I shifted by something that's curvature, sorry, that's derivative squared. But if I added here something that's higher order in derivatives, then that would manifest itself at higher orders. But of course, I would have to then keep track of the change, as Arunaba said, also to order y squared. Be a bit painful, but yes, you could adjust some of the coefficients that way. Yep.
Okay.
But of course, it becomes less and less powerful because there are more and more options of terms.
Yeah.
But it's still a good idea to do it. I agree. I mean, because you want to be at the minimal set. So, okay, so let's count powers for graviton amplitudes. So we now do something like we did previously. So we have curly E number of external particles, which are now gravitons. And this is going to be some process. So from n alpha here to n beta over there. And so we have epsilon is equal to n alpha plus n beta external gravitons. And so So let me see. So now let me just remind you. I'm going to actually, just for the sake of power counting, I'm going to keep some of the terms that we actually eliminated. But I want to just write to remind you. So we have m Planck squared over 2 r plus, say, a1 Riemann squared. Okay, plus dot 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 plus b1 over m squared r cubed. I want to keep those. I could have also just kept the higher order ones, but I want to keep those because I want to illustrate to you this structure now. So what we have is schematically, okay. So I could illustrate this structure at the higher orders, but it's easier to illustrate it at lower orders because I have to write fewer terms. So schematically, what we have is we have now, let's expand this around flat space, right? So we have this eta, which of course is 1. Now from the first term, okay, from this term, okay, we get the thing that we constructed a couple of lectures ago. So we get things that are like of order m Planck squared h box h plus, and then we have m Planck squared h squared box h plus, and so on. So we get an expansion, this expansion here, in our physical field, the graviton. And we have higher and higher powers of the graviton, but we always have only 2 derivatives. Okay, we discussed this fact quite a bit. So we basically went the other way, right? We started by with this structure, and we showed that it resums into this term. But now, of course, we also have the terms. So we have something like, we have here, let's see. So we have something like m Planck squared h d squared h, and this should be with some coefficient over m squared. Let me just say this goes like 1 over m squared. Okay, plus m Planck squared. Let's say, for example, right? So, for example, we could have something like this acting on h cubed plus dot dot dot. Okay, so this is now an expansion which has arbitrary powers of h, but has 4 derivatives acting. So this is something like 4 derivative terms. So this, if you want, is 2 derivative terms. And of course, and so on. So what we get is the structure is that we get, if you want, interactions with arbitrary powers of h mu nu, and ascending numbers of derivatives d, right? And so let me do the final thing, which is usually customary. What we do is, okay, now I've said this before, but you see this kinetic term here has an m Planck squared in front of it, but typically we rescale things such that the kinetic term is canonically normalized just order 1. And this rescaling is basically eta mu nu plus h mu nu, sorry, goes to eta mu nu plus 1 over m Planck, not squared, m Planck h mu nu. Okay, maybe, yeah, and this is a rescaling. Okay, I don't want to call this h tilde now. It's just, you know what I mean. I'm just going to redefine h, but I'm not going to use tildes to have to avoid clutter. So then this LEFT is of the form, well, it's h D'Alembert on h plus 1 over m Planck h squared D'Alembert on h, and so on. Okay, plus 1 over m squared times h D'Alembert squared on h plus 1 over m Planck delta squared h cubed. Oops, sorry. Plus and so on. Okay, so now the important thing is that this goes like I put out m squared times m Planck squared, and then I have the following structure. I have h over m Planck, right? Then I have something like p over m squared h over m Planck, right? I'm just counting now numbers of, if you want, derivatives. So the h over m Planck compensated by the m Planck squared out here. And then I have two derivatives, p over m squared. So I compensate this by the m squared out here. So this is really this term, okay? But I've written it explicitly with the various quantities. Plus, then I have something like h over m Planck squared, p over m squared, h over m Planck. Plus higher orders. I guess this was this term here, okay, h over m Planck squared, this and this, and compensated by this guy out here. And so I have precisely the following structure. So this let this be the last formula that I write. The interaction EFT is going to be, I have a overall m squared m Planck squared times a sum over all derivatives, where I have a coefficient Cn with the power m to the number of derivatives in the interaction, times the operator On, which is made up of h mu nu over m Planck squared. Okay. So m counts the number of derivatives in the interaction, number of derivatives, and MP counts the number of graviton fields. Okay, and then this prefactor m squared m Planck squared is this is what we used to call f, you know, to the 4. This is the overall. This is the overall scale. Okay, so let me actually stop here, and we'll take this up after the break. But essentially, as I said, it is perfectly fine if you prefer m. Well, if you want to work in a scheme where you take your cutoff to be the Planck scale, and then this just becomes m Planck, and then you can see m Planck to the 4th is f to the 4th. But this more general structure that we also allowed for in our EFT analysis, it turns out to be very convenient for calculations, and in some contexts, such as actually the effective expansion for string theory, even necessary. But we'll get to revisit this. Okay, so I'd like to stop here. Unfortunately, I have to do something quickly now before the next lecture. So let us postpone all questions to the end, but make a note of your questions, because I don't want to, like, you know, suppress the questions. Just make a note now, and I'll see you at 11:15. Okay. Thanks, guys. See ya.
Thank you.
So actually, I mean, it's up to you. We can also have some questions now. I'm sorry, I just had to go. You know how it is, home office. But if you have, if you'd rather wait until the end, it's really up to you. Okay, can you hear me, guys?
Yes, we are there.
Yeah, okay, good. Well, that's something at least. Right, so then let's go on. So what we have is basically, we have this analogous result. Let me write it now really in the form analogous to what we wrote in our general EFT discussion. A, E, and we were writing, you know, so we're putting a tilde on here because we were writing this amplitude with the delta function removed. Okay, we called that guy a tilde. And so what we have is we have m squared, we have m Planck squared, and we have 1 over m Planck to the number of external gravitons. We have m over 4 pi m Planck to the 2L, and we have E over M to the power P. So how did I get to this? Well, there's two ways. One is to go again through this same power counting, so we can write down what does a vertex contribute. So wait, so we were here, right? So we had this characterization of our EFT expansion. We know what the kinetic term is, so we know what the propagator is, and we know how to classify all the interactions regarding their powers of derivatives and regarding the powers of our parameters, m Planck and little m. But of course, I also have done this analysis for you in general, where this m was, well, the derivative counting parameter, this m Planck is what we called V there, right? We said that we count the numbers of times the fundamental field appears, we called that thing V. And then we had this guy, we called it F. And so then you can go back to our general analysis and you can just adapt it, right? So we looked at the superficial divergence of a diagram in dimensional regularization using precisely these kind of quantities, only we gave them other letters. And what we ended up with was precisely this thing, okay, where we had, well, what we used to call V to the power of the total number of external fields. Our loop counting parameter was what in our convention now was little m over m Planck, okay, to the 2 power of loops. We had this E over m to the P, and then we had the overall F to the 4 here, okay? So this is one way of arriving to that, arriving at this result. But you could, of course, also, as I said, you could do it again from scratch. You could write down how does the graviton propagator scale with momentum, how does each vertex scale with momentum, and then do the dim reg, and you would also arrive, of course, you would also arrive at this result. Okay, but of course, this has to be completed by the definition of P, which hasn't changed, but let me just write it. It was 2 plus twice the number of loops plus the sum over the vertices d minus 2 VI d, where d is the number of derivatives and I is the number of lines that go in. And I put a prime here on the sum because I'm not summing over the kinetic term. We only summed over the interactions, but okay, that's what we did always. So VID was a vertex with I lines of H mu nu and D factors of P if you want, or derivatives, factors of the momentum P. So it goes like P to the D. And then this, okay, this sigma prime, just to be clear, is we just omit kinetic term from counting. But this was naturally the case in our EFT discussion anyway. Okay, so good. So let's see, let's make some notes and then let's go and calculate. So first of all, we have a power of E over M to the 2 plus 2L plus this sum primed D minus 2 VID. So we have only positive powers of E over M. That's good. I think we noted this kind of thing also already in our discussion. Okay, so then the second note is one that I have mentioned a few times, but let me write it down. Okay, so the fact that the case of 2 scales, namely where you have M, P, and M, which are distinct, is important. Oops. Single page is important It's important in string theory and in ADS-CFD. And at least ADS-CFT is going to be our next topic. And how does it manifest itself there? Well, MP remains the Planck mass. So nothing special to say there. But M, this little m, actually will be something like 1 over the length of a string. This is like this, so it's related to the string length. So it's sort of related to the string tension, really. And this is saying that in the context of a string theory, there's really two ways in which it can deviate from a graviton effective field theory. Of a theory of ordinary particles. One is, of course, there's Planck mass physics, and the second is that Planck scale physics. The second is that the string itself has a finite length. So at some scale, you should also see the fact that you no longer have point particle interactions, but some sort of non-locality. And that scale is, of course, the mass scale that's associated to the length of the string. So the mass scale associated to the length of the string is 1 over Ls. And so you really have a double expansion in the Planck mass and the string length. And in the holographic context, it turns out that the second parameter, which we would like to interpret as some kind of string length, also plays a role there. So in holography, I guess we'll have to discuss it in more detail when we get there, but just for those who have already heard about it, of course, we still have the Planck mass, which is related to the number of degrees of freedom per site. But then we also have the 't-Hooft coupling of the gauge theory, and that is basically going to be related to the second parameter, little m. So also naturally there you have a double expansion in 2 parameters in this EFT. So then third remark, 3, we have gravity apparently at low energies, right? That follows simply from our analysis of those terms, basically symmetries. So we have gravity at low energies. And what do we mean? Well, we want to be way below the Planck mass, and we want to be way below this mass m. And this gravity at low energy is weakly coupled. Okay, just in the sense that the parameter E over m is very small. And so in some sense, this is just a manifestation of the fact that whenever EFTs apply, they are weakly coupled. But what we will see from our specific analysis that will follow is that gravity, in fact, is extremely weakly coupled. And so it's in a particularly good EFT, if you want. So now let's just look at some examples. So some low order contributions. So the leading contribution is when L is equal to 0 and then P is equal to 2. Okay, and so what can we get there? Well, the only way that you can get P is equal to 2 is basically if you have 2 derivatives. So these are, and no loops. So these are all tree level 2 derivative diagrams, which is of course the simply full expansion of this term. And so this is classical GR, right? But then maybe we say A, B, what is going to be true about the first corrections? Okay, now we're getting into interesting territory. So there's 2 possibilities. So either we are at 1 loop, L is equal to 1, but then VID has to be 0 for all terms that have more than 2 derivatives. Let's see, right? So we have this P, okay? So the leading order contribution was L is equal to 0, so that P is equal to 2. Okay, so that told us that we have no loop and we have only the Einstein-Hilbert vertices, okay, because D is equal to 2 there. Okay, and that obviously is the smallest P that we can possibly get, and this is going to be the leading order in this expansion. Now, let's go to one higher order. So what we can do is we can add one loop. So now P is equal to 4, and we say we have nothing from this term. Okay, so this is going to be one loop Einstein-Hilbert, right? Because if I say I get nothing from this term, this means that I exclude all of the vertices that are at higher order in the derivative expansion than Einstein-Hilbert. Okay, so I get one loop Einstein-Hilbert. This is what I was saying here. We can say i.e. one loop Einstein-Hilbert. However, this is not the only way that we can get there. We can also make sure that we are at 0 loops and we get this to be 2. So for example, we take one term only that has 4 derivatives, right? Because then this here will give me a factor of 2 as well. So we can say L is equal to 0. Vi4 is equal to 1. And Vi2 is still arbitrary. Oops, that's not how you write arbitrary. Yes. Arbitrary. And all other VID are 0. So what does this mean? This means we have one curvature squared interaction. Plus any number of, let me call them Einstein-Hilbert type interactions. Okay. So now we're getting into the interesting territory. Okay, so let me just say it again. Okay, so from our EFT expansion now applied to just the Einstein-Hilbert effective theory, if you want, we have actually deduced, right? I mean, in some sense, we knew this intuitively, but we have deduced, and indeed, it's weakly coupled. The leading order, so A, it's weakly coupled. B, the leading order contribution is just tree diagrams made from classical, from the Einstein-Hilbert vertices. So this is classical GR. So by the way, I mean, this might sound trivial, but this is a derivation using quantum field theory that classical Einstein-Hilbert at low energies is a good description of this theory. Okay, that's not a trivial fact. Thirdly, now we look at what are the first corrections, and we find that now, for consistency, there are two types of corrections. One is if you just treat Einstein-Hilbert as a quantum theory and you add one loop diagrams and you add nothing else. So remember, we were using this EFT as a mechanism that selects for us which terms in the derivative expansion contribute to what kind of diagrams. And the statement is, if you want the leading order correction to classical GR and you want it to be at one loop, then Einstein-Hilbert is the only kind of interaction that contributes, and no other higher curvature interaction contributes to such kinds of diagrams. That's great news. However, there's slightly bad news, which is that there is also another way of contributing at the same order of correction to the classical GR, and that's where you stay at tree level, but you include one of the higher derivative terms. Okay, and so what I'm going to show you now is going to be something which, well, at least I find it is quite subtle, but once you understand it, you know, it's sort of obvious. But that this would seem like, okay, we're in trouble because we know we know the only thing that is really fixed for us is this. We don't know what the coefficient is of this higher curvature term. This is an arbitrary thing, and that we said would come from matching to UV, which we don't know. So in some sense, this seems that already we're unable to calculate the first quantum correction to classical GR, okay? But I will now demonstrate to you that this is actually not the case. And the reason, okay, this is the important bit, the reason is that the kind of physics that comes from this correction is fundamentally different from the kind of physics that comes from this kind of correction. And the important bit is that this leads to a modification of the long range force behavior. So this is something that really changes the infrared properties of GR, whereas this thing leads to something that's extremely local and gives you basically a UV modification. So this will be something like a very finite range interaction, like a delta function even. And this thing will give you something that propagates over long distances, and that leads to a modification of the Newton potential. And this modification of the Newton potential is therefore uniquely fixed by the Einstein-Hilbert term, by this kind of correction, okay? But to get there, we need to go somewhat into the detail of this calculation. But I hope that at least a preview of that logic is somewhat clear. Two types of corrections, one which we manifestly control because it only depends on the lowest order term, and that's Einstein-Hilbert, nothing to do about it. The second, which depends on the possible higher curvature correction, whose coefficient we don't control. Okay.
Julian, I have a question.
Yes.
So why do we now have curvature squared terms? We defined them in a way in the last lecture. Is that because now we're discussing matter coupling as well?
Yes, that's a very good point, precisely, because what I said the word Newton potential, so we're going to have like external masses. Yes, so very good. That's an important clarification that I should have made. Okay. However, you know, the logic stands. I mean, even if we didn't have meta couplings, we just would have to go to higher orders and we would have a similar discussion there. Okay. So, yes. I had some comment here on the meta couplings number 5, but that was essentially done. So 5, let's see. Well, what did I want to say? Yes, with meta couplings. You have one loop physical divergence, which, however, we can deal with using this EFT logic. So we are interested in, like, so say we're interested in the case of like external non-relativistic matter. External non-relativistic matter, such as, for example, stars and planets. And well, I have this discussion here that the external scale is therefore dominated by mass, not momenta. Okay, I don't know how useful this is, but we'll see in practice what that means. External scale dominated by mass, not momenta. Right, this is just basically the non-relativistic statement that they're non-relativistic sources. Okay, so I'm actually going to write down some source now. I think we just need to embark on this calculation now. It's a little bit painful, but it's worth doing it. I may not be able to completely finish it today. I think it's probably better not to rush it. But it won't take a lot of our time next time. Yes, it's probably better. I was sort of hoping to start the ADS part next time, but let's spend maybe 15 minutes or so next time on tidying up or finishing up this calculation. Let me also comment that what I'm giving you here is basically, I'm giving you now what is hopefully a conceptual and somewhat technical overview of a calculation that is actually straightforward, but tedious. And the details of this calculation are actually in 2 papers, one review and one paper, which I have already uploaded to Moodle. So one is by, well, both of them involve Donahue. He wrote a review, but also there is a paper by, well, I don't want to say the names now of the authors because I guess I forget some of them, but maybe I'll write an email about which of the papers in the Moodle I mean. Okay, and this does really every single diagram with every single regularization and so on in full detail. And I would actually urge you that sort of as a homework, read that paper. I hope that it will become very readable once we've gone through the treatment here. But, you know, going through every single diagram, you will see that because, you know, gravity is not that much harder in this treatment than, for example, electromagnetism, but it does have a lot more indices and it becomes a lot more complicated for really no particularly enlightening reason, okay? So please, as a homework, go and read this paper in detail, and of course also feel free to ask me questions about it. But I hope anyway that this lecture will be the guide that you need in order to understand all that's there. So let's do predictions of gravity EFT. Good. Right. And we will also comment, of course, on its eventual downfall, meaning where actually does this approach break down, and well, what do we do to go beyond that? So let's look at the external source. Namely, some mass density rho of R, which is equal to, well, let's say we have a bunch of masses like our sun and maybe Earth. So masses that are basically concentrated at some R minus Ri. So now let me remind you really how in a quantum field theory you can define the potential. So definition of the potential. This is actually something which is something that's treated in like any sort of quantum mechanics undergraduate course, but I'll remind you. So let's consider the following diagram. For example, let's consider something like you have F, this T matrix, initial state, right, being scattered into a final state, and we've subtracted already the trivial part unity. So what I mean is, what do I mean? I mean that S minus this trivial one is T. Okay, so basically we're calculating an S matrix element. And let's look at it in the context where you have the exchange here of a graviton. Let's say, let's just give the example of where it's tree level. P1 primed, P1, P2, P2 primed. And this just at the level of formal definitions, this is equal to the delta, the momentum conserving delta function. So P is of course P1 plus P2, P primed is P1 prime plus P2 primed, times some matrix element M. Let's say we give this guy some exchange momentum Q. And this is this matrix element, and this is the matrix element which we will calculate in our EFT. Of course, this definition of the potential has nothing to do with EFT, okay? This is just, I will tell you in a second how this gives you a potential. This is just something general that you can do in quantum field theory. So now this defines for us, if you want, minus 2 pi times delta of E minus E primed times F V of Q I. And why is that? That's because if you calculate this thing in quantum mechanics, then in the Born approximation, okay, we know that this scattering process basically gives you, so it's Born approximation in quantum mechanics. The scattering amplitude, or this matrix element, is precisely the Fourier transform of the potential. Fourier transform of potential. Fourier transform with respect to the momentum transfer. Okay, and so then the real space potential is just the Fourier transform of this. So V of R is then equal to, well, there has to be some normalization factors here, which becomes 2m1, 2m2 times d3q divided by 2 pi cubed e to the I q dot r of m of q. Okay, and that's just by essentially, well, we calculate this process in quantum field theory, then we remind ourselves how in non-relativistic quantum mechanics we would have defined, well, we would have calculated this process, and we remind ourselves that it's just the Fourier transform of the potential with respect to the momentum transfer. And so we calculate basically this thing, we take its non-relativistic limit, because we are interested, as I said, in non-relativistic external sources like the sun or the earth. And from that, we just take the inverse Fourier transform if you want, and that gives us a definition of the real space potential. Okay, this is, for example, also how you can calculate the Coulomb potential starting in quantum electrodynamics. I'm sure you've seen it, the photon exchange. In fact, I think in some earlier lecture, I even demonstrated how to do it. But okay, this just as a reminder.
Sorry, Julian, I have a question.
Yes.
Yeah, when you say Born approximation in quantum mechanics, what is the correspondence with the QFT approximation? Is that a weakly coupling approximation?
Is this the
weak coupling approximation? It's like assuming weak coupling?
Yes, I think that's correct. Yep.
Okay, thanks.
So, so let me first give you the schematic answer that will tell us how to distinguish actually between these long range effects and the short range effects. And then let's go into the kind of diagrams that contribute. So I'll write it here anyway. So full calculation is tedious. So see this paper or these papers by Donahue. I think this is how you write his name, Donahue. Schematically, what happens? Schematically, this m of q squared, or m of q, is going to take the form, well, there's some calculable coefficient, and it goes like 1 over q squared. So this is going to be, this is just going to be the classical piece. And this will give you a potential that goes like, oops, like 1 over r. So this is really the Newton potential. And this comes from, obviously, as we said, zero loop, only Einstein-Hilbert interactions. But then we get corrections which are non-analytic in the exchanged momentum. So that there are things that go like square root of q squared with some coefficient k1. And there is something that goes like k0 times the logarithm of length of Q squared. These are things which are, as you see, non-analytic in Q squared, and they lead to long-range forces or long-range modifications. So they go like 1 over r to some power, which will be typically a higher power than this, but nevertheless 1 over r to some power. And then finally, we will get things that are analytic in Q squared, but of higher orders than this. And these will lead to short range, namely things that go like delta 3 of r type modifications to the potential. So obviously, what I'm going to do for you is I'm going to show how to calculate these coefficients ki, okay? Also how to get these terms. But I just wanted to now, again, underline the different, qualitatively different contributions that you get. So you get the classical piece, okay, that one is not too difficult. But then we get the one loop Einstein-Hilbert. These are the only ones which can lead to non-analytic behavior in momentum, okay? For those of you who have, calculated enough Feynman loop diagrams, this is probably obvious to you. So this is one loop Einstein-Hilbert, and we can extract from those the non-analytic contributions, and because it's only the non-analytic contributions that give you something that falls like a power law and that is relatively speaking long range. And then there are things that come from the curvature squared interactions or higher, which are analytic in Q squared, which give us short range modifications. Adrian, I see your question. Let me just say that one more thing. So the key really to this prediction of the low energy EFT based on Einstein-Hilbert was to isolate these terms. And that's what we're going to do. Yep.
Yeah, so sorry, I think I don't see directly the relation between the non-analyticity and the long-range character of the interaction.
That's easy to do. You just do the Fourier transform and you will find, so for example, if you have something that's like a constant, right here, it's the simplest to see is a constant. What's the Fourier transform of 1? It's a delta function. And if you do the Fourier transform of these guys, you will just see that you get something that goes like 1 over r cubed, for example.
I see. Mm-hmm.
So in fact, in this review of Donahue, which is in fact on this issue is a little bit shorter than what I'm saying. So as opposed to the original papers, he does this exercise where he just takes the different kind of terms that you might expect, and he inverse Fourier transforms them, and he shows what structure in momentum space you get. And so you will see that the non-analytic structure corresponds to some long-range power here.
All right, thank you.
Yeah. So good. So let's calculate at least this guy now. Okay. So this is the tree diagram where I'm using Einstein-Hilbert. Okay. So we have well, I've drawn this diagram. Well, let's draw it again. Why not? Q, so we have some mass source here. We have a mass source there. P1 prime, P2 prime. And so we have I amplitude at tree level. Okay, so this is going to be now the energy momentum tensor that corresponds to this mass source here. So T mu nu 1. Okay, oops, I've already written the 1. Of P1 primed M1. We have the Graviton propagator, which has 4 indices, nu, alpha, beta. And let me just write it as 1 over q squared times this index structure. And then we have, no, what's going on here? We have this T mu nu 2, which depends on P2 primed and M2. Well, essentially, what you do is that, of course, because it's a non-relativistic source, it's only the 0, 0 component that is appreciable. And oops, sorry, these are alpha beta indices. Okay, sorry. And the same is true here. Okay, so you project basically on the 0, 0, 0 component here. Each of them gives you a factor of the mass. So this becomes, well, there's a factor of -4 pi. We don't really care about that. Times the mass 1. This is the contribution from this guy. And this is the contribution from that guy is times mass 2. Then each of these vertices, remember, was a factor of square root of g Newton. So in total, we get a factor of g Newton. And what remains is 1 over q squared. Okay. But since we're in the non-relativistic limit, the length of this becomes 1 over the length of the 3 momentum squared. And so if we take the Fourier transform of this, we find that the tree level potential, tree, is equal to minus g Newton times m1, m2 over r, which is, of course, the Newton potential. This is not a surprise. This is what we call the classical Newton potential. Okay, good. But now let's look at the one loop corrections. So I'll have like 6 minutes officially because I started as a couple minutes late, but maybe I should only take 4 minutes. Yeah. So you have, okay. So you have things like, okay, yes. So you have things like, for example, this kind of term where, you know, you have again, P1, P2, P1 primed, P2 primed, and you propagate the graviton in a loop using this kind of vertex, okay? It turns out that this diagram gives you some number times g Newton squared, right? Because you have 4 vertices times m1, m2 times log of q squared. So this would give you a contribution of v delta v loop from the box, which if you do the calculation, it gives you minus 47 over 3 times m1, m2 over pi times g squared over r cubed. Okay, so this is a subleading correction to the Newton potential that's order g squared over r cubed. But let me just say that you have also other one loop corrections, which are, you know, like, for example, you can make a diagram like this, where you have some triangle here, okay, and then you take this kind of vertex, and this goes like g squared m1 m2 times there's some number times log of q squared, okay, plus some other number times m1 over the length of q, also non-analytic, okay. Then you have a diagrams of the kind, okay. So this goes like some number times g squared m1 m2 times log of q squared. And I suppose, let me not absolutely draw all of these diagrams because I just want to give you the one loop and I want to contrast it to the single curvature squared interaction. So the V total one loop, okay, there's more such diagrams, but V total one loop of R is actually equal to G Newton times M1, M2 over R. Okay, so I've just factored out the Newton potential, but times 3G M1 plus M2 over R plus, and this is now the really interesting bit. Well, both of them are interesting, but this is the one that I want to underline. 41 over 10 pi G H bar over R squared. And well, let me actually put this on the other page because I want to copy, paste. Because what I want to point out is that this is if you want the quantum correction. And this is actually a relativistic correction, which also comes out in this treatment. This is what you would call a post-Newtonian correction. But both of them are of the form some modification of the power law. So let me just say the last remark is that 3 diagrams from, so 1, 2, 3. 3 diagrams from R squared interactions. Okay, those contribute something like, so one might draw it like this. Okay, and I put some symbol like this, so I'm using like 3 diagram from the R squared interaction. This gives me a contribution to the potential, which goes like G M1 M2 times M1 plus M2 times the delta of R. Okay, and so the point is that this is extremely short-ranged. So if you are interested in just calculate and just the infrared of the theory, you can actually forget about this kind of correction, and you really only are interested in those corrections. And so the long-range corrections, long-range effects, entirely from non-analytic loop effects in Einstein-Hilbert. Okay, so good. Let me stop here so we can actually take some more time next time. I think what I will do is next time the lecture, I'll prepare it. I'll in the sense that I'll write down a couple of pages with all the diagrams that contribute, and I can just walk you through them to be sure that we've understood the systematics, and then we will launch into more of a discussion also that leads us to discussing the breakdown of this EFT. But for now, the thing that I want you to take home is that because of the EFT logic, we were actually able to do controlled loop calculations, okay? And then added to this, we could also tell which other higher order terms do we need to include that in principle compete with these loop interactions. That was also, you know, an important lesson that we learned from our consideration of how effective field theory works. But then the non-trivial really next thing that happens, which is really something quite wonderful about the way that EFT works, is that if you're only interested in the IR properties, then we could filter out the non-analytic corrections, and these non-analytic corrections are fully determined by Einstein-Hilbert. So this correction to the potential that we wrote down in the end, this guy, it is a prediction of our symmetry analysis, right? Because our symmetry analysis fixed the Einstein-Hilbert at lowest order, and then putting this effective field theory on top of it, gives us this unique prediction for the infrared modification. And this means it's really a strong statement. This means that any UV quantum field theory, UV quantum gravity theory that you write down that disagrees with this quantum correction must be wrong, because it follows from what we already know. I mean, we are convinced that Einstein-Hilbert is the correct classical description. We have shown that there is an EFT description, which means classical is the best is already the leading approximation plus a small quantum correction, and that quantum correction is uniquely fixed by the classical theory. So any quantum gravity theory that you work out the one loop correction to the graviton potential, you disagree with this, you're not describing our world. You might be describing something that's intellectually interesting, but it would not be our world. So this is a very strong constraint. Okay, so there was already a question. I'll stop here and I'll open for questions.
I was wondering if in this development, do we take into account also the graviton-graviton interaction?
Yes.
Okay.
So for example, there is a diagram which is, let's say there is also a diagram of this kind.
Yeah, that was
that
the
contributes. Yeah. Mm-hmm. Other questions? All right, well, seems like there are no other questions, but I think it's worth it not to rush things too much. So as I said, next time I will write down again all the diagrams, and we'll discuss those diagrams, and then because the conclusion will be the same, I guess we'll have ample opportunity to again try and ask those questions. Don't forget also as homework to read through these 2 papers there, or maybe just the one original paper. And I shall send you all an email with precisely which references is among the ones that are already in the Moodle. Okay, so enjoy the rest of your week. Bye-bye.
Thank you, bye.
Bye, thank you.